Welcome back. This is a lecture on biconditional statements, which is a part of LO5. The other parts include converse, inverse, contrapositive, and negation. So biconditional is the fifth part of LO5. Don't forget to put your name, your period on your notes, and this is when this lecture was done, Wednesday, August 15th, and Thursday, August 16th. All right, so biconditional statements, which you should recognize this prefix, bi means two. So what a biconditional statement is, it's taking two conditional statements and combining them. So it's two conditional statements combined. In fact, it's two very specific conditional statements. So it includes an original conditional statement and the original's converse. If you remember, converse means it's switched. So it includes, for example, A to B and then B to A. All right? Okay, so the symbol for biconditional is a double arrow, all right, which makes sense because it goes both ways. And the way you connect the statements is you use the words if and only if. So essentially you do statement A, if and only if, statement B, right? Because, for example, A, double arrow, B, all right? Let me do the one below to show you what I mean. So you have two statements here, A and B, and we want the biconditional statement. So what I do is I take statement A and I write, so what this is going to be is a complex number has an imaginary part. That's statement A, if and only if statement B, a complex number cannot be a real solution to an equation. Right, so just to sort of use some colors, you have statement A, right, that's the first part, and then you have statement B, which is the second part. Okay, and in the middle it says if and only if. Now, mathematicians are super lazy, so they get tired of writing if and only if a lot, which they actually use it a lot. So the shorter version you can also use is IFF. That would be considered like the abbreviation, right? If. So if you ever see IFF, they're talking about if and only if. Two F's essentially combined. Okay, so truth values are a little different than the other ones, right? You still use the same tables, but the difference is it's biconditional. So we use two tables, right? You're going to have a table for the original, and you're going to have a table for the converse. So you have the original here, and we have the converse. All right, now in order for this statement to be true, both original and converse need to be true. All right. So to be true, both have to be true. Otherwise, you're false. All right? So a note you need to notice is they're never open. Okay? All right, so if you take a look at this, now remember when you're doing truth tables, before you actually fill in the table, you need to justify whether they're true or false. So if you don't remember, a complex number is A plus BI. That's an example, right? Where it has both parts, a real part and an imaginary part. So a complex number has an imaginary part. That is true. Okay? A complex number cannot be a real solution to an equation. Well, to be a real solution, you need to be a real number. It has a real number part, but because it has this imaginary part, it's not real. So this is also true, because it says cannot be a real solution. That's correct. This cannot be a real solution to an equation. So both statements are true. So I'm going to write true, true. And then over here, it's a switch. So true, true. And if you recall, true, true will give you true, right? True, true gives you true. So the whole thing is true. And that happened because both statements are true. If this one ended up false, the whole thing would be false. If this one ended up open, the whole thing would be false. Okay? All right. Now down here we have two tables. We have A and we have B. And both are supposed to represent the table for the biconditional statement. Now just to refresh, right, your biconditional statement would say X is an odd number if and only if, so look, I used a little abbreviation, odd numbers are not divisible by 2. Okay? That's your conditional statement. Now, in order to figure out which table is the correct one, because one's correct and one's wrong, first thing you need to realize is what they did is they took their two tables and they sort of combined them into one. Because you'll see that here is the original and here is the converse, right? Here is the original and here is the converse. So rather than do them as separate tables, they combined it. Okay? All right. Well, again, before you decide on the tables, you need to decide whether each statement is true or it's false. So, C, X is an odd number. Well, that, I would say, is open, right? Because the variable would be X. We don't know what X is. X could be 3, it could be 10. It could be open, it could not be. We're not sure. So, it could be true or it could be false, so it's open. Odd numbers are not divisible by 2. Well, let's think about this. 1, no. 2, that's not an odd number. So this is true, right? Because if it's odd, it's not divisible by 2. All right. So we have open and true. So whenever it's open, you want to put a T and an F, right? So this means open, which they did that in both. And then D is true. So they put 2 T's, 1 T for each one. Okay? Now, original, you go the correct way. TT gives you true. FT should give you true. TT gives you true. FT gives you. So here, that's where they made the mistake, because false true will not give you F, it will give you T. All right, now let's keep checking. When you do the converse, you just go backwards. So TT gives you true, TF gives you false. In this case, all right, this is the correct one. All right, so this is wrong. All right, wrong table, because it made a mistake. This one's correct, and your answer is actually false, because the original was true, but the converse ended up open. And you can't be open, remember? Never open. So, because one of them was open, the whole thing ended up being false. Now, just a side note, All right, remember we keep talking about this is biconditional. There are two conditional statements. We do two tables. So you need to realize that because even though we use the words if and only if, there's actually two statements hidden in here. The first one would be if x is an odd number, then odd numbers are not divisible by 2. All right, so I'm going to kind of put the note down here, right, for you to realize that there's two statements within, right? Number one is if x is an odd number, then odd numbers are not divisible by 2. And the second statement is just the converse. If odd numbers are not divisible by 2, then x is an odd number. So instead of writing all of this out, that's why we have the words if and only if. Okay, so just realize that there are two statements within this statement. So these are the same. Okay? Okay. Last example, all right? They want to know if this is false. Now, they didn't tell me to write any statement, but so you know, you just should take this and you would add in IFF between it, or if and only if. So it would become prime numbers are divisible by 1, if and only if prime numbers are divisible by 2. However, all we want is a truth table. So I'm going to do two tables. I'm going to do one for the original and one for the converse. Okay, so we have this one and this one. Now the original goes EF, so if E then F, and the converse switches it. If F then E. All right, prime numbers are divisible by 1. True, because if you remember the definition of a prime number is that it's where a number that has the factors 1 and itself. So like the number 3, with only numbers that can multiply are 1 and 3. Prime numbers are divisible by 2. That is open, all right? Because remember, the number 3, you could do 1 and 3, so there's no 2, but the number 2, there is a 2. So even though there's only one example that proves that, it's still possible to be true and false. Okay, so E is true, but F is open. So TF, TF. Okay, so true, true gives you true. True, false gives you false. True, true gives you true. False, true gives you true. So the converse ends up true, but the original ends up open. So the whole thing is false. All right, and there you go. That is biconditional statements.